Tasks in natural language processing may employ a number of different techniques. For example, you might have statistical techniques or rule-based algorithms to perform some of your tasks, or we might use machine learning or deep learning. Both machine learning and deep learning are subsets of artificial intelligence that enable computers to learn without using explicit programming. Machine learning focuses on algorithms to learn from data. These algorithms can be relatively simple, like decision trees or linear regression, or they can be more complex, like support vector machines. In Python, we have a popular library called scikit-learn that has a lot of these algorithms for machine learning in Python. For example, we have classification algorithms, regression algorithms, and clustering algorithms that can perform different tasks related to natural language processing. In addition to other areas of AI, for example, image processing. There are also different techniques that come with this toolkit for reducing dimensionality, selecting the right model to use, and of course pre-processing data. And in natural language processing, the text does require pre-processing before we use any machine learning or deep learning models. So then, what is the difference between machine learning and deep learning? Where machine learning focuses on algorithms to learn from data, like we looked at those examples, these ML models typically involve fewer layers of processing compared to deep learning. So deep learning is going to have deeper, hence the name, layers of processing. So you can think of machine learning as the simpler workflows with fewer steps, whereas deep learning are going to become more complex with deeper steps. Deep learning is a subfield of machine learning in that sense, and it is inspired by the structure and function of the human brain. It utilizes artificial neural networks with multiple layers of interconnected nodes or neurons to process information. These layers allow for more complex feature extraction and representation that learn directly from raw data. Artificial neural networks are the core building blocks of deep learning. A quote from Gemini, which is a large language model: artificial neural networks are inspired by the structure and function of the human brain. They consist of interconnected layers of artificial neurons, which process information in a similar way to biological neurons. Unlike traditional programming, ANNs learn through training on large data sets. So I mentioned Gemini being a large language model. Gemini was trained on very large data sets. By adjusting the connections between the artificial neurons, they can identify complex patterns and relationships within the data. And this makes artificial neural networks powerful tools for tasks like image recognition, speech translation, and even generating creative texts, which a lot of the large language models are doing today. With artificial neural networks, we aim to mimic how we believe the human brain works. And this artist's image here shows a network of nerve cells, which we call neurons, and they are connected by synapses. And these synapses are believed to carry information in the form of electrical signals between these neurons in the network, and that is how we believe that the human brain works. If we look at computers, in fact, our computers themselves, we built them based on this idea and this concept of the neural network, and even at the lowest level of the hardware. So you can think of Boolean logic gates. We'll look at that for a minute. Here's a logic circuit diagram. We just want to look at the picture here, but if you're not familiar with logic gates, you can read through this Wikipedia page for an introduction. This comes up in electrical engineering classes and some computer engineering courses, because our computers are built on a series of these logic gates, and the logic gates are taking in electrical signals as inputs, passing them to individual gates, which are doing some form of processing with the signals, and then passing the output along to the next gate in the network, which does some more processing and passes it on to the next gate, and so on, all the way until you have an output. So in this example, this is a logic circuit diagram for a 4-bit carry look-ahead binary adder. So it is simply doing binary addition, so adding two inputs together. And in this particular design, it is streamlined using only 3 types of logic gates: AND, OR, and exclusive OR. So you can see these gates in here. Here's an AND gate. Here's an OR gate. Here's an exclusive OR gate. And these simple gates connected together can do some complex computation. So this very simple example here, if you look at the image and think about these gates as neurons and these connections between the gates as synapses between them, you can think about the computer and how we designed it in general based on our belief and representation of how the human brain works. So the ANN represented in this diagram on the right is a screenshot from a website called the TensorFlow Playground. And you can see in this screenshot our attempt to mimic what we believe the human brain is doing. So we have inputs, we have these nodes in between that are called, we call neurons, and ultimately we have outputs. So the inputs get processed through the neurons. At each layer, the neurons are outputting to the next layer of neurons. Those neurons are doing some computation, outputting to the next layer of neurons, and so on. So depending on how many, we call these hidden layers, depending on how many hidden layers of neurons you have, you might have any number of layers and neurons that ultimately lead to your outputs. And the outputs can be one or more outputs at this end. Here is a very simplistic diagram of an artificial neural network where we have our input layer. So here we have 1 to n inputs. Here we have a single layer with 4 neurons and an output layer, and in this case it is a single valued output. The connections, which you see coming out of each neuron to the next layer, have weights associated with them. So each connection has an associated weight as it's going into the next neuron. And here you see a fully connected network where for each neuron in the hidden layer, we're taking an input from each of the neurons in the input layer. And not depicted here are the weights on every edge, but there are weights on every one of these edges. And they might be the same or they might be different going into the different neurons on the hidden layers. And these layers, these neurons in the hidden layer, are taking the weighted sum then of its inputs and adding some kind of activation function to transform that data before outputting it to the next layer. Now you might have multiple hidden layers in here, as we saw in this diagram up here where we had multiple hidden layers of neurons, until ultimately you come to the output layer. So that is a very high-level look of an artificial neural network. And as you're learning, this TensorFlow Playground is a fun place to go and learn more about how neural networks work. So let's open this link and take a look. So the playground that we're looking at here offers a visual and interactive way to experiment with some core concepts of artificial neural networks. For instance, we can use the playground to explore the effects of different parameters applied to artificial neural networks. And you'll see as you look at this that there is a lot of different parameters you can change, from the input data, ratio of training to test data, which says how much of your input data should be used to train the model versus how much should be used to test the model. If you're going to introduce noise in the data, the real world is noisy. The data sets are typically not clean, especially in natural language processing. There's going to be a lot of what we call noise in our input data sets. And that can be in the form of, for example, spelling or grammatical errors are introducing noise to the system. Batch sizes determine how many data points are included in an epoch, where an epoch is a complete cycle, training cycle, as you're training the model, and you can train it for as many epochs as needed, or typically we'll specify up front when we're building a model how many epochs we want it to train for. You can specify a learning rate, how fast does the model learn, an activation function, any type of data regularization you want to include, the rate of that. And we have two different problem types that we can use with this playground. We have classification, which is the default, where inputs lead to distinct outputs or classes. And that is in contrast to regression, where outputs can be arbitrary real values. So just looking at the images here, classification classifies things into well-defined groups, whereas regression has real valued outputs. So let's start with classification since it's a little easier to look at. And our goal here is to train a network, an artificial neural network, to be able to predict whether a new input will fall into, for example, the orange category or the blue category. So let's choose a data set. We can look through the different data sets and see what the input data set looks like. Here's a data set where we want blue data points in the inner circle and orange data points in the outer circle. Here's a data set where the input is divided into quadrants, and we see two quadrants that we want to identify as one type, and we colored it orange, and the other two quadrants that we want to identify as another type, and we've colored those blue. Here is the simplest data set of these inputs, where you have, in this area, the data points are all blue, and in this area, they should all be labeled as orange. And so this is the input data. The idea here is that we're training the model on this input data, and when the model is given new data, for example, a new data point given its coordinates, the model can predict what color that new data point should be. So if you can imagine the point -4 and 5, if we added this new data point, the model would likely classify it in this blue area. But as you're looking at the different shades of colors here, The background colors are representing how data is going to be classified and how strongly it's going to fall in that classification. So for example, a dark blue is going to classify as blue. And when we first pull this up, what we're seeing in the background coloration is a random guess. So we haven't trained anything yet. And then here's another more complex data set. So if we look at this first one and we see the one that includes the 4 different sections, and we see our random guess, this data is actually representing exclusive OR, which is one of the gates we just looked at in our logic gate diagram. So these background colors are representing a function, and the function is defined by the lines separating the colors. If we go ahead and run this, we start to see our model trying to form a function that represents the color separation well. And we can see after so many epochs, it finally settles on a good form where all of the blue is being classified appropriately, all of the orange is being classified appropriately. So here you imagine a new point being inserted, and that new point will be classified based on the background color here. So that is just how this visual representation works. So you start out with seeing a background that represents a random guess of what the function looks like and how prediction will proceed from there. And then as you run the model, you can see that the function becomes better defined and better able to make predictions based on the input data it was trained on. So let's look at different ways that we can play with this. I'm going to first take it down to 0 hidden layers. So this is just input mapped to output. And if I run this, you'll see that the neural network is not able to form any guess as to what the function is that separates these classes, orange and blue, because there's no neurons in this network at this point. So let's stop that, reset, go back. Let's add a hidden layer. So now we have one hidden layer that has 2 neurons. So now we have our neural network that has 2 internal neurons that will be operating to try and train this model. So let's run that, see what it looks like. And we see now it's actually attempting to make a guess where before it wasn't even trying, but the guess is not good. It's trying to guess with simple straight lines what the different classes are, what the areas are, the function, and how that should be written, and that's not working with 2 neurons. So let's add more neurons and see if we can improve on that. We can add another neuron, start over again, and play. And now with that added neuron, we see the network actually starting to make a better guess at what the function is that describes the classes of this input data. So let's continue. Let's add another hidden layer. Run it again. So adding another hidden layer, we more quickly came to a close approximation of what we're looking for. But we're seeing some jitteriness here. So we're seeing some uncertainty in the network. So that is not going to be a very precise model. Let's go back and add more neurons. So now we have 2 hidden layers with 3 neurons in one, 2 in the other, so that's 5 neurons. We continue playing with this. Let's add an additional neuron to the first hidden layer. And now we're starting to see something that is closer to resembling what we may have intuitively thought when we first looked at this data set, was that it's divided into 4 distinct quadrants, and the neural network is learning that. and it's doing a better job of learning with the layers and neurons that we have. We can continue adding layers and neurons, but understanding that there is certainly a cost associated with that, a computation cost and sometimes a space cost on your hardware. And so I don't really like how this one is not giving us the clear, what we might expect to see is a clear 4 sections, so a clear segmentation into 4 sections, especially knowing that the input data is representative of exclusive OR. There's going to be 4 distinct sections that we want to see. So let's see what else we can do to try and get this model to come closer to the predictive function that we want to see. So we've tried adding neurons, we've tried adding hidden layers. I'm going to go ahead and take one of those hidden layers out. Just run it with the 4 neurons in one layer. So as you're watching this, you can see that the ANN is trying to fit to the data, and it's doing this by adjusting weights and biases on its connections between the neurons based on errors between its predictions and the actual data points. So when we are training the neural network, we are providing it with training data, and the training data says, this is what the inputs are and this is what the outputs should be, and now you need to learn how to identify and guess those outputs, predict those outputs accurately based on the inputs. So in the training mode, you're given the outputs, and so you can adjust your weights on your edges and see how close you get to the correct prediction. And then you can go back and readjust those weights when you're off. So those weights and biases are being adjusted in the background. I'm going to go ahead and add that other hidden layer back in. And so far this is the closest we've got, but it's still not perfect. So what else can we change? And one of the things we can change here is the activation function. So without really talking about what activation functions are, you can do some exploration on your own to try and determine, based on this input data set, which activation function might work better. So leaving all other things the same, let's try a different activation function. And we see this activation function is trying to separate the space into 2 distinct areas where we clearly wanted 4, so that one isn't working well. I believe this is the activation function we started with by default, which got us much closer to the function that we were looking for. We'll try another activation function. Let's make sure we've restarted here. And we see, given this model, that the activation function, in this case, seems to be coming to a correct formulation, albeit slower than the first one we tried. And finally, we'll look at the last activation function. And so as we watch this play over the epochs, you can think about what do these activation functions mean, and how do we choose the correct activation function? So that's a discussion for another day. Right now we just want to familiarize ourselves with the playground and playing with the playground, but we can see and make some determinations on our own just by observing the outputs of playing with the playground. So this linear activation function has been running for a couple thousand epochs and continuing, and you can see that it is clearly not even forming a prediction about how to classify data points. So the training is really just failing there. And maybe you've intuitively come to the conclusion that, well, linear is a straight line, and this data is not classified in a linear fashion. That is, you cannot draw a straight line through this graph in any way such that one class is on one side of the line and one class is on the other side of the line. That is, you won't see any way to draw a straight line where you have blue on one side of the line and orange on the other side of the line. And we know that's what linear means, straight line. So we know that linear, of course, is not going to work. So that kind of should intuitively give you an idea of what these activation functions are doing. But like I said, that is beyond the scope of this tutorial. But it's a good introduction to get you started thinking about how different activation functions are creating these different predicted models. Another thing that we can play with, let's go back to this TANH, which I think was one of the closer ones, activation function, so we'll stop that there. Another thing you can play with is the learning rate. So we can have smaller or larger learning rates, where larger learning rates are going to learn faster. So see how I'm resetting and playing, and that faster learning rate came to a formulation more quickly, in fact, very quickly, but maybe didn't come to the best outcome. So there is a trade-off there between learning speed and the stability of the model. So a higher learning rate does allow for faster adjustments, so that did allow us to come very quickly to an outcome. But it could lead to some instability, so it's not necessarily going to be the best outcome. And I hope you're also observing that as we start and rerun this, we don't get exactly the same result every time, right? So this is just the neural network learning on the input data. This is not a brute force process. It is not learning the exact same way and looking at all possible combinations of data every single time. It's simply going through a learning process of making a guess and then adjusting weights and biases on the different edges based on how close that guess came to being correct. So you can think about the activation functions and choosing the correct activation function. When we talk about learning rates, it's really a matter of a trade-off. Do you need the learning to happen faster, or do you care more about the learning and the ultimate model being more stable and having better performance and predictability? And depending on the problem that you're trying to solve, you may go one way or the other based on that. Maybe fast is more important than accurate. Maybe accurate's more important than fast. We go to a slow learning rate here, and we'll watch this play for a minute. This one's going to learn much slower. And of course, as it's learning, you can see the loss rates. So this is a measure of how well the model is performing. And in fact, when you are creating your own models and evaluating them, you will create these loss charts for test and training loss to evaluate the goodness of your model. So we can see that the slower learning rate is in fact taking longer, but ultimately should lead us to a better outcome. And that doesn't necessarily mean it always will, but we expect that a slower learning rate is going to lead to a better outcome. But of course, that's going to be a lot more expensive. So the slow learning rate did not seem to do too much better than a medium rate, but certainly the fast rate was not great. And then different activation functions gave us different outcomes as well. So I'll leave it to you to test on the different data inputs, changing the activation functions, the learning rate, and also remembering that you can change the number of hidden layers. and the number of neurons in the hidden layers to see if you can improve the performance of the model in terms of speed and in terms of how well it is capturing the pattern that you're seeing in the input data. And one final note, we talked about the linear activation function and how that is certainly not going to work for nonlinear data. That is really the point of these activation functions, because different activation functions work better for different problems. And an activation function is taking the weighted sum of the inputs and applying a nonlinear transformation. So other than the linear activation function, these others are applying some kind of nonlinear data transformation to generate the neuron's output. And this nonlinearity is important because linear models can only learn linear relationships, like our first example here, or our simplest example here. Linear models can only learn linear relationships between the input and the output. And so these activation functions introduce nonlinearity. So that allows the network to model more complex relationships that cannot be represented by a straight line. So think about that as you are testing different data inputs against different activation functions. And just try and get a feel for, without even looking up, I would recommend you first try and get a feel for what each of the functions is doing before you look up the definition of the function, because this is part of the science. And that's what I love about this ability to tinker with a neural network in this playground here, is this is really giving you the ability to do science, whereas with machine learning and deep learning and artificial intelligence in general, we're typically doing engineering. If you dive right into this playground, you have an opportunity to do science, where you're making observations and determinations based on those observations. So it's a fun way to learn about artificial neural networks and watch as the artificial neural networks are essentially learning through trial and error, adjusting their internal connections to minimize prediction errors as they go. So that is a very brief introduction to artificial neural networks. And again, those are the baseline for all of our deep learning. But as we talk about in different videos in this series on natural language processing, for example, in natural language translation, a neural network in general is one model you can use, but then we looked at the transformer model, which was a specialization of a neural network, which included a concept of attention that ultimately ended up with a neural network, a specialized neural network that did a better job for some natural language processing tasks.